In question 3, we want to draw the resulting heap after executing the sequence of method calls. To begin, let's go over the basic characteristics of the data structure. Every node in the min heap must be less than or equal to its children, and a heap must always be complete, which means all available positions for elements are filled except for possibly the last row, which must be filled from left to right. The green heap on the left is complete, but the pink heap on the right is not, since the left child in the root's right subtree is empty. To insert into a heap, you place the node at the next available spot in the bottom row of the tree. If the row is full, we just make a new row. Then we swap the node with its parent until the heap upholds the min heap property, which is just the invariant that parent nodes must be less than or equal to their children. To delete the minimum node in a heap, which will always be the root, you swap the root with the bottom rightmost position of the tree. Delete the bottom node and bubble down the root until the min heap property is satisfied. Additionally, we can represent heaps as arrays with the following indexing scheme. So the root of the tree will be in position 1 of the array. The left child of a node at index n is at index 2n. The right child of a node at index n is at position 2n plus 1. And the parent of a node at position n is at position n over 2. So going back to our problem, we start off with an empty heap and insert f. So now it just has that one element. We then insert h, which is placed in the next available spot. We then insert d, which again is placed in the next available spot, but we cannot terminate yet because the min heap property is not yet satisfied, since d comes before f. So in this case, we need to bubble up d until the condition is met, which is just equivalent to swapping d and f. Then we insert b, which is placed at the next available position. And again, the min heap property is not upheld yet, so we bubble b up, this time with 2 swaps. Then we insert c, which is placed as the right child of d. And again, we bubble up c. Then we call remove min, which entails swapping the root with the bottommost right child and deleting that child. We then bubble down the new root until the min heap property is upheld. So in this example, we swap d with c, and c becomes our new root. Our last operation is another remove min. So we again swap the root with the bottommost right child and delete that child. And then bubble down the new root until we get a perfect heap. So we just swap d and h here. And this is our final heap structure.